Have you ever wondered if we could teach a computer to really understand language? I mean, not just by crunching huge amounts of data, but by actually getting the fundamental logic of it all. Well, today we're diving into a surprisingly elegant, almost beautiful solution to one of the toughest problems in linguistics and computer science.
So let's start with a really big question. Is language, with all its poetry and nuance, is it just a type of formal logic? Could the structure of a sentence actually be solved like a math problem? It's a wild idea, but it's one that has driven researchers for decades, and it has led to some absolutely incredible breakthroughs.
Okay, first things first, we have to get a handle on the puzzle itself. The real challenge here is creating a formal, mathematical system that can actually describe these super complex, almost fluid rules of human language. I mean, how on earth do you turn grammar into an algorithm?
And this, right here, just nails the problem perfectly. We as humans instantly know one of these sentences is right and the other is just nonsense. But how does a computer know that? We're not even talking about the meaning of the words yet. It's all about the order, the syntax. So any system we build has to solve this fundamental problem of structure first.
Now, this isn't some new puzzle. Brilliant minds have been chipping away at this for a long time, using a really fascinating tool called categorial logic. The basic idea? Treat words kind of like chemical elements that can only combine in very specific, predictable ways to form a stable molecule, or, in our case, a sentence.
The journey to our solution is really a story of evolution. It started with what are called classical categorial grammars, which gave these types to words. Then came the lambic calculus, a huge leap forward that formalized grammar as a real type of logic. It was incredibly powerful, but man, was it complex to work with. And all that complexity really set the stage for a new idea, a major breakthrough in simplification from the very same guy, Johann Lambic.
And here is exactly why that breakthrough was so important. Trying to parse a sentence with the old lambic calculus was like trying to read some ridiculously complicated sprawling blueprint. Yeah, it worked, but it was a mess. The new way, with pregroup grammars, turned that entire process into a clean, linear assembly line. It was just a radical simplification.
And that brings us to the hero of our story today, pregroup grammars. They somehow managed to just slice right through all that complexity while keeping all of the logical power. It's pretty amazing.
Okay, I know that technical definition looks intense, so let's just break it down. It's describing an algebraic system where every element, just think of it as a word's type, has these special things called adjoints. Honestly, you can just think of them as connectors that have an opposite. The entire system is built on one simple, powerful idea. When a word's type meets its opposite connector, they cancel each other out. That's it!
To make this even clearer, let's use an analogy that I think makes this whole thing click. Imagine word types are like Lego bricks. Each brick has specific connectors, the bumps on top and the holes on the bottom. A sentence is grammatically correct only if you can line up all the word bricks and they snap together perfectly with no leftover connectors.
So how does this whole Lego system actually work in practice? Let's pop the hood and see exactly how these types snap together to validate a sentence that we all know and understand. All right, here we go. Our sentence, cats chase mice. First step, we assign the types. Cats and mice are simple nouns, so they get the type N. The verb chase is a little more complex. Its type, NR/N/L, is basically saying, hey, I need a noun to my left and I need a noun to my right. If I get both of those, I will form a sentence, S. Step 2, we just line them up. And now for the magic in step 3, cancellation. The N from cats snaps perfectly into that NR connector on chase, and the N from mice snaps into the NL connector. Poof, they cancel out. And what are we left with in the end? Just S, the type for a complete sentence. It worked.
The engine that drives this whole thing is this incredibly simple, elegant formula. This is like the law of physics for our Lego bricks. It just says that a left connector AL and a brick A cancel out, and a brick A and a right connector AR cancel out. That's literally it. This one simple algebraic rule is what makes the whole system so unbelievably efficient.
But, just checking if grammar is correct is only half the battle. The real goal is to actually understand the meaning. And this is where pregroup grammars get even more powerful.
See, the process does way more than just give a thumbs up or a thumbs down on the grammar. The way the Lego bricks snap together, that exact sequence of cancellations, it actually creates a recipe. It tells the computer precisely how to combine the meanings of the individual words to build the meaning of the entire sentence.
And that recipe can be used in a couple of different ways. For instance, with vector space semantics, each word's meaning is a vector in some high-dimensional space, and the grammar's recipe tells you exactly how to combine them. Or you could use functional semantics, where each word's meaning is a logical formula, and the recipe builds them all into one big, coherent logical statement. The system is just as powerful as it is flexible.
So this all brings us to the ultimate payoff. Why does this simplification, this elegance, matter so much in the real world? Well, it all comes down to one word: efficiency.
And just look at this slide. It shows the benefit with stunning clarity. The computational complexity, which is basically just how hard a computer has to work to parse a sentence, is dramatically lower for pre-group grammars compared to those older systems. And in computing, lower complexity means faster results, and using way less energy and money.
And here is the absolute kicker. This massive gain in efficiency doesn't come at the cost of power. Not at all. It's been proven that pre-group grammars are formally equivalent to context-free grammars, which are like the bedrock, the gold standard for parsing in computer science. So you literally get the best of both worlds, the beautiful simplicity of the new system with the proven power of the old ones.
So we end up right back where we began, with a question. The story of pre-group grammars is all about finding a simple, beautiful core hidden inside a massively complex problem. And it really makes you wonder, if the logic of something as messy as human language can be simplified this elegantly, what other complex systems are out there just waiting for a similar breakthrough?